All right, so in this video, we're going to go over basically naming and transition metals. So nomenclature, if you see the term nomenclature, that just basically means naming. So we're going to go over how we actually, once we write those compounds like we did in that last video, how we actually properly name them. Okay, so we're going to start off with our rules. So naming monatomic compounds. Again, remember mono means one. Okay, so that means you're basically dealing with one element from the positive side and one element from the negative side. So rule number one is cations are always first. So that was the same in our formulas as well. So if I had my example Na with a +1 and chlorine with a -1, when I put those together, I know they're going to be balanced, okay, because I see a +1 and a -1, so they're just going to simply put NaCl. So your cation was always first in the formula, and it's always going to be first in the name as well. So anions will be last. Now, rule number two is a cation's name will never change. Okay, so we will not alter it at all. You just leave it the same, the way it says on the periodic table. Then rule number three is a monatomic single, basically a monatomic again means single. A monatomic anion will always end in IDE. So if it's just an element by itself, okay, meaning it's not one of the polyatomics on that list, it will always end in IDE. We will change its name. So our example was calcium, so Ca, and chlorine, Cl2. So calcium is the cation, so that means it's going to be first, and then chlorine is the anion. So remember, we do not change the cation at all, so it's simply calcium. Now, instead of me just writing out calcium, chlorine, which just sounds like you just slap two elements together, you're just saying random names, okay, we're going to change that anion's name. Okay, so instead of chlorine, it's now going to end in IDE, so it's going to be called chloride. Okay, so now it just sounds a little more fancy. Okay, so CaCl2 is considered calcium chloride. Okay, so when I say monatomic and I say single, since there is two here, that's still considered monatomic because it's still just chlorine. Okay, so it does not have to be just one chlorine to be considered monatomic. Now, if I were to write something like this, so CaClO3, that is no longer a monatomic. Now you're dealing with a polyatomic right there, which would be chlorate. Okay, now these are going to be your common anion names, so if you want to write these down, okay, you can. This is simply just how you convert those names. So carbon becomes carbide, nitrogen becomes nitride, oxygen is oxide, fluorine is fluoride, chlorine is chloride, phosphorus is phosphide. Okay, and then iodine is iodide, and bromine is bromide, and sulfur is sulfide. So these are the ones you're going to see quite a bit. Okay, so if you need to write those down to help you out, that's perfectly fine. So more examples. So say I have something like NaCl. Okay, so Na is sodium, and chlorine is going to be my anion. So instead of me writing out sodium chlorine, it's going to be sodium chloride. Now my next example is MgI2. So magnesium is my cation. So remember, you never touch the first one, just read it like you do off the periodic table. And then instead of me writing magnesium iodine, it's going to be magnesium iodide. Then Al2O3 is aluminum oxide, Li3N is lithium nitride, and then KBr is potassium bromide. So again, cannot stress that enough, is we never change the name of the cation, and then anions will usually change their name and ends in IDE. Okay, so now what we're going to do is we're going to talk about transition metals, because that's the next part of doing our bonds is transition metals. So that whole group, basically, so I'm going to go back up here to my periodic table to show you what those transition metals are again. So starting right here at 3B and going all the way to that staircase basically is called your transition metals. That means we don't know their charge. So if we need to recap those charges again, remember over here on the far right side, that is 0, -1, -2, -3, -4. Oh, sorry, that's a plus or -4. And then +3, jump all the way over here, it's +2 and +1. Now, this is important because just because it is in group 4 does not mean that every single one of these has a charge of plus or -4. Okay, so basically anything above that staircase or anything to the right of that staircase is going to follow that trend. Everything below it can go a different route. So that means 10 can have something different than a positive or -4. It is still a part of that transition metal. So again, your transition metals are basically from group 3B all the way to the staircase, meaning that their charge can be anything, +1, +2, +3, +4, +5, etc., based on who they're bonded with. So let's come back down to our transition metal notes. Okay, your transition metals, so again, they start in your D group. Okay, so starting right after that group 2A, and they go to the staircase. Now, the only elements that never change their charges in that group is silver, zinc, and aluminum. So this would be a good thing to write on your periodic table, is I would come back up here to my periodic table, and I would say, let me clear this up a little bit. Ag is going to be a +1, so silver is +1, zinc is +2, and aluminum is +3. Those will never change. They will always stay that way. So even though they're in the transition group, those are the only three that are the exception. So I would write that down as a +1, +2, +3. Okay, now let's come back down to our notes. So everything besides those three, when we start doing naming, will have to have a Roman numeral to state the charge. So since iron, so my example is iron 3 nitride. Now, iron can have something different. It could be iron 2, it could be iron 1, it could be iron 4. So we have to put a Roman numeral to tell you that that is the charge of that particular iron. So that 3 right here tells me that iron has a charge of +3. It does not tell me how many irons I have. It just tells me that iron has a charge of +3. Okay, so if I were to write this out, I would say that iron, which is Fe, has a charge of +3, and nitrogen has a charge of -3. So I can see that those are balanced. So if I wanted to write the chemical formula for iron nitride, it would just be FeN. Okay, so you can see here that that 3 does not tell me that I have 3 irons. It just tells me the charge of that particular iron. Now, Roman numerals are only used for transition metals. So if I have something that's in group 1A, so group 1 is always going to be considered a +1. So you don't need to tell me that there's a Roman numeral for +1 because I know everything in that group is always +1. It is only for transition metals. Okay, so if it is in one of those groups, 1A, 2A, all the way through 8A, okay, you do not need to write a period. You do not need to tell me what the charge is through a Roman numeral. Okay, so again, they tell us the charge, not how many you have. This is probably the number one mistake I see from students is when I give them something like that, so I say iron 3 nitride, the first thing they do is they write Fe3N. Okay, that would be incorrect. That tells me the charge, not how many. Okay, so once you know the charge, then you can figure out how many you actually have. So again, do not use these for groups 1A, 2A, or silver, zinc, and aluminum. Silver, zinc, and aluminum will always be +1, +2, +3. Now, if you need to recap on your Roman numerals, 1 is simply an I, 2 would be II, 3 would be III, 4 is IV, so watch out for this because I see this is probably the number one confusion is IV, 5 is V, 6 is VI, and 7 is VII. That's as high as you basically need to go. So just again, pay attention between 4 and 6. Those are two different things. So if the I becomes before the V, that's 4. So the way I think of that is I before V, so B4, 4. Okay, so whatever you kind of need to do to help you memorize those. Okay, so transition metals, so always find the charge of the anion to determine the metal's charge. So since transition metals can be anything, the thing that can help you is the anion it's paired with. So my example is write the cation in anion for FeCl2. So in order to find, so step 1 is in order for me to find the charge of iron, I need to see who it's bonded with. So I'm going to take a look at chlorine. Now chlorine is in group 7A. Which means it has a charge of -1, because it's always going to have a charge of -1. Okay, so that means you can do, I'm going to write this down here, so FeCl2. Okay, so since I have 2 chlorines, that would give me a total charge of -2. Okay, so my total charge for this chlorine over here would be a -2. Now, if I only have 1 iron to balance out that -2, okay, that would mean that iron would have to be a +2 charge. So any formula we give you is balanced, always. So if my total chlorine charge is a -2, and I only have 1 iron to balance it out, it would have to be a +2 to be considered balanced. So that means the charge of my iron is a +2. So my answer would be Fe +2 and Cl with a -1. So you can do the reverse crisscross. Okay, so again, just check your periodic table, make sure it works. So I would take the 2 from the chlorine to the iron, and I would take this imaginary 1 on the iron to the chlorine. Okay, so you would have to make sure that is chlorine, does it have a charge of -1? If you reverse crisscross and that anion matches the periodic table's charge, then you're good. If it doesn't, I would probably take a look at that because it might be a reduced formula. Okay, so again, like we just talked about, you can try the reverse crisscross method. So example is find the cation and anion for CuBr2. Okay, so take the imaginary 1 from the copper to the top. So I'm going to write this up here. So CuBr2. I'm going to take this imaginary 1 from copper up here to bromine. And I'm going to take the 2 from bromine up here to copper. Now what I'm going to do is, since bromine has a -1 up here, I'm going to check my periodic table. Does bromine on the periodic table have a charge of -1? If it does, then you're good to go. Okay, so that means, so again, this is why I put it in bold here, is check the periodic table first to see if you're correct. So that means bromine has a charge of -1. Okay, now you can take the 2 to the copper, so that means copper, so copper is going to have a charge of +2. So again, if you need to check yourself, okay, so if a copper has a charge of +2 and only have 1 of them, that gives me a +2 charge. And then if I have 2 bromines and each one has a -1 charge, that's going to be a -2. So since these numbers match, that means this is a balanced out formula. Okay, so that means copper has a charge of +2, so your answer would be charge of +2, and bromine has a charge of -1. So again, you can always check yourself just by totaling them up and making sure it's the same answer. Okay, so now more examples is write the cation, anion, and chemical formula for copper 1 oxide. So I'm asking you to split them up first, tell me the charges of each individual piece, and then I want you to write the formula for the entire thing. And I just gave you a name. Okay, so copper 1 oxide. So remember, that Roman numeral tells us that copper has a charge of +1. So there's part of my answer right there. So I know that Cu is a +1 charge. Now, if you look on the periodic table, oxygen has a charge of -2. There's another part of my answer. So there's my cation and anion. So there's the first 2 parts of my answer right there. Now we're going to have to make sure the formula is balanced. So if I look, there's a +1 and a -2. Those are not balanced. So you would do the crisscross method. So you take the 2 to the copper and then the 1 to the oxygen. So that means your correct balanced formula would be Cu2O. A little more examples. So now what I want you to do is I want you to write the cation, anion, and chemical name of Pb3P4. Okay, so I'm going to take a look at this. I'm going to see that Pb is lead, and lead is a transition metal, so that means I do not know what the charge of lead is. It could be anything based off who it's bonded with. So what I'm going to do is I'm going to look at phosphorus first. Okay, so I'm going to look up phosphorus on the periodic table, and it has a charge of -3. So there's part of my answer right there is that my anion is phosphorus, and it has a charge of -3. Okay, that means, so since I can do the reverse crisscross, so if I have this, so Pb3P4, if I take this 3 up to this phosphorus, and that means it has a charge of -3, okay, since that matches the periodic table, that means the reverse crisscross is good to go. Okay, so I'm going to take that 3 up here. Okay, so that means phosphorus is a charge of -3, so that means I'm going to take this 4 up to the lead. So that means lead has a charge of +4. Okay, so there's the other part of my answer right there, is lead has a charge of +4. Now, if you want to check yourself as far as math-wise goes, that's perfectly fine. That's probably a good idea to do on some of these. So if lead has a charge of +4 and there's 3 of them, 3 times 4 gives me +12. And if I have a charge of -3 for phosphorus and I have 4 of them, so -3 times 4 gives me a -12. Since these numbers match, that means that is good to go. That works. Now the name. So remember, you cannot just put lead phosphate. Okay, because lead is a transition metal, it has to have the Roman numeral in the name. So again, if you are dealing with a transition metal, it has to have the Roman numeral in the name because you have to tell me what the charge of lead is. So since lead has a charge of +4, we're going to write lead IV. So remember, IV is your 4, and then phosphide. Okay, so again, if you have an anion, you cannot just write lead for phosphorus. Okay, your anion's name is, if you have a monatomic, it's just going to be phosphide. So your correct answer would be lead for phosphide. Now, naming with polyatomics. So if you refer to your polyatomic list, you have to know these for the test. So if you need to go back to that video and watch how to basically memorize those, okay, there is different naming rules for polyatomics. Now, polyatomics, so number one, polyatomics, first of all, means many. They will always end in ate and ite. Okay, so ate and ite. Okay, so that means a polyatomic. So use that list. So the polyatomic is going to look like this. So chlorate would be ClO3 with a -1. That's my example right here. Now, if it's monatomic anions, they're going to just end in IDE. So if anytime it's just an element by itself, like chlorine here, okay, so chlorine is a -1 charge, that is going to be chloride. Okay, so you have to pay attention that if it's just chlorine by itself, it means it doesn't have an oxygen attached to it. That means it's going to end in IDE. Now, there are some prefixes and suffixes that, again, that I talked about in that video that you add to the name if we are adding oxygens or taking away oxygens. So if you add something like per to the beginning of the name, so ClO4, that would be considered perchlorate. Okay, so our original was chlorate. That was our original. Now, if you add an oxygen, okay, you're still going to end in ate, but now you have to add per to it. So you see how you went from ClO3 to ClO4? That's why it's perchlorate. Now, as soon as you go to ite, this is probably the number one mistake, is I see I have students that want to put IDE for ide and ite, ITE. So again, I cannot stress this enough, is that IDE means that there is only chlorine. No oxygens, nothing else attached to it. If you put ite, that means you are still dealing with a polyatomic. Okay, so this would be chlorite. Because chlorate was ClO3. Chlorite is ClO2. So since I took away that oxygen, I lost one oxygen, my name is going to go from ate to ite. Now, if I take away two oxygens, okay, that means I'm still going to end in ite. But now I have to add hypo to the beginning. Okay, so again, one of the examples I used in my last video is the term hypoglycemia. So that means your blood sugar is too low. Okay, so hypo means, so hypoglycemia is too low. So that means you lost two oxygens. So I'm going to take my original chlorate. If I take away two oxygens, this now becomes hypochlorite. Okay, so again, so you see how I never used IDE for anything that was polyatomic. So if it is monatomic by itself, it's IDE. If it's polyatomic, it can either end in ate and ite, depending on if you lost or gained. If you have the same amount of oxygens, lost oxygens, gained oxygens, and we also deal with some prefixes. Again, it's not too bad, it just takes a lot of practice. Now, some more examples. So write out the ions and the name for iron. So this is FeClO3 2. So one, we see that iron is a transition metal. Okay, it's in that transition group. So that means we're going to need to look at chlorate to find the charge. So if you look on your polyatomic list, chlorate has a charge of -1. So that means that there are two of them. So since I have two chlorates, there is a total charge of -2. Okay, so that means if I only have one iron to balance out that -2 charge, that would mean my iron charge would have to be a +2 to be balanced. So this one would also work as far as your reverse crisscross. So if you write FeClO3 with a 2, I would take this one, imaginary 1 from the iron and take this up to chlorate, and I would see, does this match my polyatomic list? Which it does. If you look on the polyatomic list, chlorate has a charge of -1. That means I can take this 2 from the chlorate up here to the iron, which is going to give me a +2 charge. So that means my cation by itself is going to be Fe with a +2. My anion is going to be simply chlorate, so it's going to be ClO3 with a -1. And now when I want to write the name, so since iron is a transition metal, I have to put the Roman numeral. Since iron has a charge of 2, you're going to write iron 2 chlorate. So be careful with this because iron 2 chlorate, okay, is the formula right up here. If I were to write something like iron 2 chloride, iron 2 chloride would look something like this, so FeCl2. So remember that IDE is only for monatomic. So there's a reason why I keep repeating this, because this is probably one of the biggest mistakes that I see year to year. Okay, so let's check another example. So write out the ions in formula for magnesium acetate. So acetate is on your polyatomic list. So if you are struggling to find something on your periodic table, check your polyatomic list first. Okay, because sometimes you'll be searching for something that's not on that periodic table. It's actually on your polyatomic list. So there's a little trick for you, is always check your polyatomic list first, and if you can't find it on there, then you can go over to your periodic table. Okay, so I'm going to look up magnesium, and it is in group 2A. So that means magnesium has a charge of +2. And then acetate is on your periodic table, and that is the big one. That's the C2H3O2 with a -1 charge. So I can see that magnesium has a charge of +2 and acetate has a charge of -1, so these are not balanced, so you can do the crisscross method. So take the 1 down to the magnesium and the 2 down to acetate. Okay, so that means we're going to need 2 acetates. So first of all, I know my cation is Mg +2, we just found that, and we know that our anion is the C2H3O2 with a -1. And when we put those together, again, if I need more polyatomics, you have to make sure that you are using your parentheses. Okay, so don't write C2H3O22. Okay, that just makes it look like you need 22 oxygens. So I put that whole acetate in parentheses, and then I put a 2 on the end of it. So that would be your correct balance formula right there. Okay, so hopefully that kind of helped out with the name. So my next videos are going to basically be doing some of the homework and balancing and naming. So hopefully that'll help out as well.